Whereas throughout most of history, it might have been debatable that our mathematics systems lacked some external validity. So while men, mostly men, were scribbling on their papers in dimly lit rooms by candlelight, figuring out algebra or calculus, it might have lacked some sort of practical application. And so for the general public to have faith in that system as having value, I think was a stretch, to the extent even that certain types of mathematics and mathematical and scientific ideas were criminalized at points through history. In the past 100 years or so, we've seen rapid expansion and development of technologies that give that external validity, that give us that tangible proof that our paper-based mathematical and physical scientific systems have direct and practical application off that paper-based world there. And so there's external validity now, which is objective and undeniable. And parts of the population perhaps are still lagging in understanding that math always has a direct application in the real world. Even if it seems like what we're working with in algebra or number theory or something is very abstract and has no real practical application in our lives. In fact, that's not quite true. There's hundreds, if not nearly infinite applications of even the simplest or most abstract mathematical principles in our daily lives. And certainly if we're dealing with computer programs and things, computers are making calculations all the time. If we're looking at the way bodies interact with one another, or the way, should we say, matter interacts with other pieces of matter, then there are always physical forces interplaying. If we're looking at uniform motion, for example, if we're traveling in an airplane or a car or a boat, or even if we're throwing a ball or something in a direction, and there's some wind, right, interacting on there's maybe some headwind or tailwind or some other forces acting on our motion, then we'll have to adjust. Even driving in the car, if we're driving down the road in this direction and we feel a crosswind, the car will move and we have to adjust the steering wheel. Right? So when dealing with things that require more precision, like flying an airplane, these things, they can't be intuitive. If you're driving down the road now and you feel a cross breeze, then you can just kind of intuitively turn the wheel a little bit. Or if a football kicker is trying to kick a goal and there's a cross breeze one way or the other, or a headwind or a tailwind, then he or she can kind of intuitively adjust and make the angle such that he'll make the goal still. But when dealing with marine travel, like a big tanker or something in a current, or especially air travel, say we're traveling at 600 kilometers or 600 miles per hour in a northwesterly direction here. If north is up on our Cartesian plane here, we're traveling at 600 miles per hour in a northwesterly direction, and there's also a north wind at 10 miles per hour. Then over the long haul, that's going to move us off our course. So we'll have to adjust for that. And if we don't, then we're going to end up in a completely different place. So say a pilot takes off and he's traveling at 600 miles per hour in a northwesterly direction because that's where the destination is, but fails to consider this 10-mile-an-hour tailwind or 10-mile-an-hour northward wind there, then he or she's going to end up in a completely different place. So if we consider the blue one here, U, we can say that U has a magnitude of 600, right? That's the length of a vector. And then our coordinates, remember from the unit circle, if we start out with a plane here and we have that unit circle, then the radius of the unit circle is 1. And it's just a circle, but it's going to tell us how sine and cosine respond, or how sine and cosine behave as we move from the x-axis in a counterclockwise direction around 360 degrees. Wherever we lie on the unit circle, our point there on the circumference is cosine of theta. If this inscribed central angle is theta, and sine theta. So the x component here is cosine, and the y component is sine. And then we're doing something very similar here with vectors, but since our radius here is always 1, then it's just cosine and sine to find that point on the circumference there. If we're dealing with vectors, we need to multiply by the magnitude because our length is no longer just 1. In fact, it's, in this case, 600. So if we say that u is equal to 600 times the, what would be that point on the unit circle, that will give us the scale, 600 times cosine 45 and sine 45. Right, and then v, we'll call v here the red one. V is our wind. And u and v are typical names for vectors. You can name them whatever you like. U and v are pretty much the standard names. That's our magnitude, which is 10, heading north. And so we've got cosine of 90 degrees, moving, again, counterclockwise from the x-axis. North then would be 90. West would be, or sorry, moving in a northeasterly direction. I believe I said northwest. West would be 180 degrees. South would be 270, and then back to the x-axis there for east. Right, so cosine 90 and sine 90. And so that should be pretty simple. And finally, where we'll end up if we don't take into account that, that change in direction due to the wind is u plus v. And so that's going to be our coordinate here. So we'll find the ground speed, but first let's find where we are in relation to where we want to end up. 600 times cosine 45. I'm going to have to use a calculator here. 600 times cosine 45 is 424.26. And then cosine 90 is going to be 0. The x component at 90 degrees is 0. So we're going to get 424.26 for our x component there. And then we'll get 600 times sine 45 plus 10 times sine 90. Sine 90 on our unit circle here is 1. Our coordinate then is 0, 1. That's our order there. And so we'll add 10 times 90 to that. Sine 45 times 600 is, again, 424. And now if you remember from early geometry, we've got a 45, 45 right triangle. And so we've got these same values here, A, and then we've got A here 2. Right? And so it makes sense that sine 45 and cosine 45 and sine 45 would be the same. 424.26, we're going to add to that 10 because it's 10 times our magnitude here times sine 90, so 434.26. And so that's our coordinate. Now to find the ground speed, what we need to do is take the square root of these squared, and so we'll take the square root of u of x squared and y squared here, the square root of 424.26 squared plus this plus 434.26 squared, and that's the same as our Pythagorean theorem. Pythagorean theorem, remember, is a squared plus b squared. So now we're not working with a 45-45 right triangle because we've been blown off course. And we've got this theta here. Now, but we know the legs here is, this is the x component, that's the y component. And so we know that this h here, that hypotenuse squared is equal to x squared plus y squared. And then we can use that to find theta. So in finding first our magnitude here, our ground speed, right, we're going to just do some quick algebra. So the square root of, and we need to use a calculator here, 424.26 squared plus 434.26 squared. And that's 607. So this is our magnitude of u plus v. Magnitude of u plus v. And that's equal to 607 we'll call it 11 miles per hour. And so that northern wind has blown us a little off course, and it's also given us a little bit of added speed, because if we're moving northeast, we do have a northern component here, which is our y component, and so it is adding to our speed, our ground speed. It's getting us there faster, but it's also blowing us off course. And so then finally, if we wanted to find the angle, where did we end up with regards to where we wanted to? We're going to use a tangent here, and so we found the hypotenuse, or that magnitude, by using the Pythagorean Theorem. If we took tangent of theta, then we would get the opposite over the adjacent, or y over x. And so in this case, this is the y, this is the x, and so we can just take the tangent. We'll take the inverse tangent. We know that tangent theta equals y over x. So we'll take the inverse tangent of y over x, 434.26 divided by 424.26. And we get about 45.667 degrees. And so then we find that theta here, this is the angle between the x-axis and our new vector, which is taking into consideration, again, the northern wind there. So we got 45.667 degrees. And depending on how far we go, that difference in ground speed and angle may not blow us significantly off course, but if the wind were a little bit heavier, a little bit stronger at points, or if we're going very far, right, then it's going to be a significant difference, right? So if we're going 100 miles or something, we can figure out how far it's going to blow us off course by doing a little bit of the same type of math. If we were going 1,000 or 10,000 miles, it's certainly going to be even more. So what this means here is that for every hour that we travel, we're going 424.26 miles north, 424.26 miles east if we're traveling in a northeasterly direction. And so if we then change that angle from 40, even just 45.00 to 45.667, for every hour that we travel at now 607.11 miles per hour, with that new bearing, that new heading, then we're traveling an additional 10 miles north. So we're going to miss our target by 10 miles to north for every hour that we travel. And so even in a 1 hour trip, which is a short plane trip, we're missing our mark by 10 miles to the north, right? Given this situation where we want to go northeast, we'll be facing a northerly wind, we're going to miss our mark by 10 miles. And so we need to adjust then, start out by flying in a more easterly direction, east of north, such that we would end up in the right spot. Especially in a long haul flight, we could miss our mark by an entire city or even a state, certainly a county, if we don't adjust our flight path so as to go aim ourselves further south from where we actually want to head, and then let the wind do the rest. So again, the main idea here is that we're seeing application in the real world of this unit circle, the Pythagorean Theorem, tangent, cosine, sine, and again, we're taking that mathematics system more and more every day now from the paper-based world that it was in the past, where people didn't really have a clear understanding of its concrete value. And now we're putting that into action in the real world that gives it external validity, which should help gain more understanding of math having practical value, having real-world value, not just being something kooky that we learn in school that has absolutely no relevance to our real-world life. Okay? Thank you.